Welcome to this comprehensive lecture on the fundamentals of biomolecules. Today, we are going to explore the fascinating mechanism of enzyme action. We will discover exactly how these tiny biological machines keep us alive by speeding up chemical reactions that would otherwise take years to complete. Let us dive right in. To truly understand enzymes, imagine you are trying to push a massive, heavy boulder over a very tall hill. It takes an enormous amount of energy, sweat, and physical effort just to reach the peak. But what if a helpful friend came along and dug a smooth, straight tunnel right through the middle of that hill for you? You still start at the exact same place and end at the exact same place, but the journey requires much less effort. In the human body, enzymes act exactly like that helpful tunnel digger, finding an easier path for chemical reactions. Now that we have our tunnel analogy in mind, let us look at the actual biochemistry. That tall hill we just talked about represents the activation energy. This is the absolute minimum energy required to force a chemical reaction to start. At the very top of this energy hill is the transition state, which is the most unstable, awkward, and high-energy phase of the reaction. Enzymes work by specifically stabilizing this awkward intermediate phase. By doing so, they effectively lower the activation energy required, allowing the reaction to proceed effortlessly and quickly. So, how exactly does the enzyme manage to stabilize this high-energy transition state? It happens when a specific target molecule, known as the substrate, binds to a special pocket on the enzyme called the active site. Historically, scientists proposed a lock-and-key model, suggesting this fit was perfectly rigid and exact from the start. However, we now know the induced fit model is much more accurate. The enzyme actually hugs the substrate, changing its own shape slightly to force the chemical reaction to happen, perfectly accommodating the transition state. Before we move on to the mathematics, let us visualize this tunnel effect. Look at this energy profile. The horizontal axis represents the progress of the reaction, and the vertical axis represents free energy. The solid red curve is our tall hill, the uncatalyzed reaction with a massive activation energy. The dashed blue curve is the enzyme's tunnel. Notice how the starting reactants and ending products are at the exact same energy levels, but the peak we must climb is drastically reduced. That difference is the energy saved by the enzyme. Seeing this massive drop in energy on the graph brings us to an important question. Why does this mechanism matter so much for us? Without enzymes, breaking down the sugar from your lunch to get energy would take years. With enzymes, it takes fractions of a second. Furthermore, understanding this mechanism is the absolute foundation of modern medicine. Many common drugs, like pain relievers and antibiotics, work by intentionally blocking the active sites of specific enzymes. If we did not deeply understand this binding mechanism, these life-saving therapies simply would not exist. Now that we understand the biological importance of enzymes, let us look at the mathematics governing this incredible speed. The speed of a reaction is defined by a modified Arrhenius equation. Here, the symbol K is the rate constant, telling us exactly how fast the reaction goes. A is the pre-exponential factor, representing how often molecules collide correctly. Delta G double dagger is the activation energy. R is the universal gas constant, and T is the absolute temperature in Kelvin. Because the activation energy is in a negative exponent, Lowering its value makes the entire term much larger. This means the reaction rate explodes exponentially. This exponential relationship we just saw leads us to a specific formula for calculating exactly how much an enzyme speeds up a reaction. We call this the rate enhancement factor. It is equal to the mathematical constant E raised to the power of delta delta G double dagger divided by R times T. Here, delta delta G double dagger represents the exact amount of energy saved by the enzyme. It is simply the difference between the uncatalyzed and catalyzed activation energies. As we will see in a moment, this simple exponential function is the absolute key to understanding the true power of biological catalysts. Let us see this formula in action with a concrete example. Suppose an enzyme lowers the activation energy by 15,000 joules per mole at a normal body temperature of 310 Kelvin. We want to find the rate enhancement. First, we multiply the gas constant, 8.314, by the temperature, giving 2577.34. Next, we divide our energy drop by this value to get an exponent of 5.82. Finally, e to the power of 5.82 gives us approximately 337. The enzyme makes the reaction 337 times faster. Now that we have successfully used the rate enhancement formula to find a numerical answer, let us understand exactly where it comes from. We start our derivation by writing the modified Arrhenius equation twice. First, we write it for the uncatalyzed reaction, using its specific high activation energy. Then, we write the exact same equation for the catalyzed reaction, using its much lower activation energy. To find out exactly how many times faster the catalyzed reaction is compared to the uncatalyzed one, we simply need to set up a mathematical ratio, dividing the catalyzed rate constant by the uncatalyzed rate constant. Continuing our derivation, we substitute the two Arrhenius equations into our ratio. Because the pre-exponential factor A is the same for both, it cancels out completely. Using the rules of exponents, we can combine the terms by subtracting the catalyzed activation energy from the uncatalyzed activation energy. We define this difference as delta delta G double dagger, the energy saved by the enzyme. And just like that, we arrive at our final rate enhancement formula. The math perfectly mirrors the biological reality. So, we have proven our formula holds. This brings us to an interesting clinical scenario. What happens if a patient has a high fever? Let us recalculate using the exact same enzyme, but at a feverish temperature of 313 Kelvin. We multiply our gas constant by the new temperature to get 2602.28. Dividing our 15,000 joule energy drop by this new denominator gives a slightly smaller exponent of 5.76. Calculating e to this power gives a rate enhancement of approximately 317. Let us pause and interpret the physical meaning of that final answer. At normal temperature, the enhancement was 337. During a fever, it dropped to 317. Why? Because at higher temperatures, there is more ambient thermal energy available. This extra heat already helps push more molecules over the activation energy hill on their own. Therefore, while the enzyme's tunnel is still absolutely vital for survival, the relative boost it provides is slightly smaller when the body is running hot. We have covered a lot of ground today. Let us review the key takeaways. First, Enzymes work by finding an easier, lower energy pathway for chemical reactions, specifically by stabilizing the transition state at their active sites. Second, this tiny molecular intervention lowers the activation energy, which, according to the Arrhenius equation, results in an exponential increase in reaction speed. Finally, understanding this mechanism is the absolute foundation of biochemistry and pharmacology, proving that working smarter is always better than working harder. Thank you for watching.